In this exercise, we'll study some oscillation that may appear in inertial units. They are called the Schuler oscillation. We'll consider, to understand the phenomenon, we'll consider the Earth, which is considered as static. So there is no rotation, just a sphere. And we put an inertial unit inside the blue robot, fixed like this. So we'll call it R1, and R1 will always be fixed inside this exercise. The radius of the Earth is R, and we put the inertial unit at this position. So the Euler angles are all equal to 0, as in the figure. The first question is what are the values that are collected by the inertial unit? So recall that the inertial unit is able to collect some acceleration and some rotation rate. So for this, let us recall that the inertial unit, like this, is the box which is inside this robot, and as an input what is able to fill with accelerometers. So it corresponds to a measured, the acceleration that are measured, and they are expressed inside the robot frame. And also we measure the rotation vector R, also expressed in the robot frame. The output of the inertial unit are the position P, the Euler angle phi theta MC, and also the speed VR. So to obtain this, we have to integrate this state equation. All the reasoning we'll have here will be in the plane. So it means that the robot, which is represented blue, has only one angle which corresponds to the pitch. So it means that here the pitch of the robot is called theta. So in this representation here, theta is equal to 0, but also phi theta MC. So what about the measurement vector? Here in the Earth we have the gravity like this, and if we are far, the gravity becomes smaller, like this, and it depends of the position P, so it corresponds to G of P. So when we are here for the blue robot, the inertial unit is able to feel an acceleration in the opposite direction like this. So since this corresponds to X, this to Z, and here corresponds to Y, which is not represented here, then the measure acceleration corresponding to this vector corresponds to A measure expressed in the robot frame. So note that the transformation to go from this frame to this frame corresponds to the Euler matrix, and here the Euler matrix corresponds to the identity, since all Euler angles are equal to 0. So we measure this J 0, 0, where this quantity is equal to something like 981. Now, since the Earth is not turning in this, is not rotating inside this exercise, there is no rotation like this. So here is the north, let's say, here's the south, there is no rotation in this direction since the Earth is considered as static, we will measure a rotation omega r equal to 0, 0, 0. So these quantities here and here are the input of the inertial unit. Question number 2. We now want to learn the inertial unit by initializing the unit at some other places. So we want to find a fake trajectory for this unit or for this robot, so that it believes that it stays in R1, so fixed. It should feel exactly the same acceleration and the same rotation. So in this question we ask to find such a trajectory. Of course, the initialization for the angle are the same, just the position should be different. To represent everything in the plane, we also assume that we'll find this trajectory in the plane y equals 0, as it was the case in the picture. So for this, we have to establish the state equation for the fake trajectory. So for instance, we will put the robot in some other places. Let's say, for instance, here. It should have exactly the same Euler angles, just the position differs. And if we put it like this, we can understand that the acceleration, if it is fixed, the acceleration it will feel will be like this. So it will be able to see the difference. But if we move this fake robot if we accelerate like this, then the composition of the two may be like this, and he will have the feeling, he may have the feeling that it is here. So we need to find this trajectory, and we'll see that they will find some oscillation. We try to prove some oscillation like this. And it is a trajectory we want to compute. So we'll start from this inertial unit, since it is the way he computes its trajectory. And this and this are the same as it was in the static case. So this and this. Just the initial condition differs. So if I take this equation, first I know that phi, theta, and psi cannot change. They are all equal to 0 forever. Otherwise, I will be able to measure them, but omega r is equal to 0, so they cannot move. It means that in this trajectory, the robot will always have this direction. Otherwise, I will be able to recognize it. So phi, theta, and psi are not anymore state variable, and they simplify. So I don't care anymore about this. Now r also, the Euler rotation is always equal to the identity. Moreover, since I have no rotation, this one is equal to 0. And so all this is equal to 0. And the equation of the inertial unit become P dot equal VR, VR dot equal J of P plus AR measured. P here is a position and corresponds to X, Y, and Z. Since I assume I am moving on the plane y equal to 0, this one is equal to 0. So j of p is equal to a vector I will have to fill. This vector is minus j, where j is equal to 9.1. Here I will have 0 here, and I will have, so I will explain just after, square root of x2 plus z2, and here z divided by square root of x2 plus z2. So let me explain this. If my robot near to the surface of the Earth is here, at position P, here I have x, here I have z. The angle corresponding, so this vector can has a cosine and a sine, and so since the length here of this segment correspond to the square root of x2 plus z2, the cosine and sine are given by this ratio, and if I write it, I assume that j is constant everywhere since I am moving at the surface of the Earth, which is not the case in practice as soon as I am far to the Earth, for instance. If I rewrite my state equation, I get x dot equal vx, v dot x equal j multiplied by, so recall that this is equal to j0, 0. So I obtain j1 minus by square root of x2 plus z2, z dot equal to vz, and v dot z equal to minus g z divided by square root x2 plus z2. So these are my state equation, my simplified state equation, and now I can simulate this. So for the simulation, I can use a different method, Euler method, which will not be accurate in this situation, or Wunsch-Gutta method, which is asked by the exercise. So indeed, question number 3, provide a simulation of the trajectory for this when the initialization is asked to be at p 0 and 1, and we have to give an interpretation. That's what I will do now. I propose the following Python program, which uses the library rublib. Here f of x corresponds, so x corresponds to x vx z vz, and the function we see here corresponds to this evolution function. So now we have taken for the radius of the Earth, we have taken 10 for simplicity. We have taken also a small sample time, and the initialization is R010 as asked by the exercise. So now we perform a loop, and we draw every time step, 10 step, we draw a small robot with an angle corresponding to 0, but with a position corresponding to x and z. We use a Runge-Kutta method for the integration inside the loop. So if we do this, I start with Python, I run it, and we can see here the corresponding trajectory with some oscillation that are not so easy to understand. But if the initial unit follows this fake trajectory, then it will feel exactly the same as it was fixed here. We have assumed that J is equal to 981 is constant everywhere. So the direction has been assumed to go to the center of the Earth, like this. But in practice, it is not the case, of course. If I go far, like here, J will be smaller, which has not been considered here, for simplicity. Other thing, just to understand this trajectory, we understand that if the robot would be here or here, they have to feel exactly the same acceleration. So recall that this one is able to feel an acceleration in this direction, and this one is able to feel also an acceleration in this direction. It is because what he feels comes from the gravity, which is like this, so it feels something like this, plus this acceleration, and this sum of two correspond to this vector. So everywhere, that's why we have this, we can understand these oscillations. Question number 4, I have to linearize the state equation for the fake trajectory, but the linearization should be done around R1. And then after I have to study the linear system by computing the eigenvalues and to give some possible interpretation. So I take the simplified equation, which are given here, and I have to linearize around this position, since the inertial unit knows it is around here, and this corresponds to the state vector x equal to r because of this. Then the speed corresponds to 0, since I know it is fixed, approximately fixed. Here it will be 0 and 0, so I have to linearize around this state vector, and I will get something like x dot equal a matrix A which depends on x, which corresponds to the Jacobian matrix, multiplied by x minus x bar. So I do this. So I will obtain directly in a matrix form x dot. So the first is linear. This one is linear. So I write it first. V dot v dot z equal the big matrix multiplied by x minus x bar. So x minus r 0 0 0 excuse me, v x minus 0 z minus 0, v z minus 0. So for the first line, I have 0, 1, 0, 0. For this line, which is also simple, 0, 0, 0, 1. And then for this line, I have to compute the derivative, but it is easier to compute directly the derivative at the point where I want to linearize. And if I do the computation, I obtain 0, 0, 0, 0 everywhere. For the last one, it will be different. I obtain 0, 0, minus g divided by r, 0. So this corresponds to the matrix A of x, and the stability of this system, so of the inertial unit, depends on the eigenvalues of this system. So of course it is diagonal by block. I take this block and this block, and I obtain that the characteristic polynomial P of S of this matrix is S squared due to this block and multiplied by S squared plus G divided by R. So it is a characteristic polynomial associated to this. The spectrum of this of A of x just corresponds to the roots of this polynomial, and I obtain here 0, 0, plus and minus j square root j divided by r. Oh, the solution of this differential equation will be a polynomial, so something like due to this and this, I will get some polynomial in t and t square, and this one will correspond to some sign like sine and cos of omega t, where omega corresponds to the square root of g divided by r. So this one, omega is square root of j divided by r. The frequency, so if I want to compute the period t associated to this pulsation, it will be equal to 2p square root of g of the inverse, so r divided by j. And if I compute with the radius of the Earth and j 9 a1, I obtain 5072 seconds, which corresponds to 84 minutes. So when inertial unit is badly initialized, I observe some oscillation corresponding to 84 minutes. So I come to the last question. Assuming that the inertial unit is not perfectly initialized, what can I conclude for the corresponding error propagation? Previously, I was in a situation where the robot were here, and I have found a trajectory such that the robot feel exactly the same as if it were here. Now what happened in practice is that the robot is actually here, and the inertial unit think that it is here because it is consistent for the inertial unit since it has been badly initialized. Now this corresponds to a nonlinear effect. What we see here is I have integrated a nonlinear equation. If in a linear situation I observe some oscillation like this, so of course if I assume that I am just near here, the linear effect is sufficient, and I am in this situation where I have from here to here, I just have a zoom of what happened. And this corresponds to an oscillation. If now I draw with respect to time t, z of t as represented here, I will obtain a sine function like this. And this corresponds to the Schuler period. So now, when the inertial unit is not perfectly initialized, we may find a different trajectory that are consistent, and the inertial unit can take the wrong one. In the case where the linear approximation is realistic, such as when I'm here, the inertial unit will return some unwanted oscillation, and corresponding to a period of 84 minutes, the Schuler period. So for many applications, I know that I am moving. I am not moving with this kind of oscillation, such as when I am in an aircraft. I go straight on. I do not have this kind of oscillation. I know, and I know these oscillations are dummy, and I can improve the integration method by adding a damping inside the inertial unit in order to damp the Schuler oscillation.